Okay, today we will continue this topic. We started with Hartree-Fock Method, and today we will talk about Thomas-Fermi Model. This is another approach to solving many-body Schrödinger equation. And then we will move to Hohenberg-Kohn Theorems. So this is basics of density functional theory. And it's just a reminder about our last topic. We have talked about Hartree-Fock method, and what was the idea? The idea was to take our huge complex Schrödinger equation with very huge and complex wave function, and then split this wave function into one electron wave functions. And by doing like this, you take this system, this complex system with a lot of some complex interactions, and you split it into independent particles, which moves into some field created by another particle. So this thing also called self-consistent field. And last time we on practice we have done some self-consistent field calculations, and today we will continue this calculations. So we take this wave function, we split it into a small independent wave function psi alphas, and then we just apply some rule that it should be orthogonal, and by doing some magic, we get this Hartree equation. So in the it's one particle Schrödinger equation, and we can solve it iterationally, in iteration way. From what parts it consists of? It consists of energy part, a kinetic energy part, minus 1/2 Hamiltonian squared. Then it consists of some external field. So in this case, external field is the field created by ions, by atoms, and or it can be some other external field which you want. And then we have this Hartree term. Hartree term, the R n alpha divided by R I minus R. So it's just Coulomb law for electrons, for electron interactions. And we can solve it iterationally. And we had to get psi alphas and epsilon. So from psi alphas, then we can get this electron density and alpha, and epsilon or E, it's just energy. It was one approach. And today I will tell you about another approach. So Thomas-Fermi model. It was created by Llewellyn Thomas. From his name, we can think that he is from Welsh or some from such from this part of Great Britain. And Enrico Fermi, so great scientist who created this model in the late 1920s. What was okay? I can't to my shame, I can't tell a lot about Llewellyn Thomas, but I can tell a lot about Enrico Fermi. So he is one of great scientists of last century. He got Nobel Prize when he was 37. So now it's a Nobel week, and he got in 37. Then he lived in Italy, but when Italy fall down to Mussolini and get closer to Germany, to Hitler's Germany, he moved to US, and in US he took part in the Manhattan Project. So he was one who created a nuclear bomb, and he was one who created first nuclear reactor. First nuclear reactor, Chicago Spile, was created in 1942 and 43 by Enrico Fermi. He was head of this project. So we should by our atomic energy, we should send to Enrico. And also he had created this beautiful model. So the goal is to in Hartree-Fock approximation, we took psi function and divided it into small psi functions. But here we have another approach. The goal is the same: to approximately solve the problem for an atom or ion with an electrons. So the same goal, but different method. We have some approximations. Electrons' behavior is approximated by electron gas. I will tell you what is electron gas. I think maybe you know what is it, but I will tell you on next slide what is it. Then we take some external potential which asymptotically approaches to zero as R tends to infinite. We apply this potential to our electron gas. And then we just fix the number of electrons in the system. So we have fixed number of electrons, and these electrons create electron gas in some external potential V. And how we can calculate this electron gas? We should make more assumptions. We will work in this momentum space. So it's not like x, y, z, but x, p, x, p, y, p, z. It's just momentum. I told you on practice, on laboratory work, why we choose momentum. Because we work with energy, and energy is like p squared divided by 2m, and it's very useful to use momentum when we want to calculate energy. And we tell that all electron states up to a certain momentum pf are occupied. So up to some pf, it's some p, but we can imagine that it's pf, we have all occupied states. And each state occupied by 2 electrons, because we have Pauli exclusion principle. Each state has a volume of H divided by L. H is Planck's constant. L is some size of this cell, of this state. So we just took this place and divided it into these small cells with the size H divided by L. What is H divided by L? It's uncertainty of momentum. If we will apply uncertainty principle, Heisenberg uncertainty principle, we will have delta P multiply on L delta X on some small size equals H, Planck's constant. And we have some uncertainty of momentum, and we tell that we can't deal with something inside this small size because it's under this uncertainty. But we can deal with these cubes because it's to the size of uncertainty. It's one assumption. Then we take this vector PF. It's Fermi vector, and Fermi surface, Fermi level. This is all to this thing. It also goes to Thomas-Fermi Model. We take this vector and tell that inside the sphere, with radius of this PF vector, all states are occupied. All these states are occupied by 2 electrons. And we can approximately calculate the number of electrons. What is the volume of this sphere? Volume is 4/3 PF in the power of 3. It's just volume of the sphere with radius PF. It's a Fermi momentum. And then we can calculate the number of electrons. We know that all the space filled with these states. We know a volume of the state. We can calculate it in the power of 3. And then we can divide this volume on this small volume, multiply on 2, because we have 2 electrons in each state. And then we get number of electrons. It's the number of electrons under some certain momentum PF at T equals 0. Temperature equals 0. So when we have 0 Kelvin temperature, all our electrons sit in their states inside some sphere with radius PF in momentum space. It's all in momentum space. Okay, we have this number of electrons. Then we can go to electron density, because we're working with electron gas, and we want to calculate density of this gas. I just divided N by V. V is it's concentration density. Yeah. So you take the number of electrons and divide by V. Concentration or electron density, because we are talking about gas. It's electron gas, but it's gas, and we get V from here, from this equation. We can estimate the volume of this small cube. Then we can calculate electron density, and then we can make some other simple calculations. We have electron density from here, N, and then we want to take PF. What will PF looks like? Like 3h to the power of 3 divided by 8p n, this electron density, in the power of 1/3. It's PF, our Fermi momentum vector. And then we get maximum energy. What is maximum energy of these electrons? I have told you that it's electron gas inside some potential V, and energy of this gas. It consists of kinetic energy of each electron, PF, P squared divided by 2m, plus V, plus this potential. So we get the energy of maximum energy of some electron here, because here we have this vector, and we have this. It's the energy of electron on the surface of the sphere, the maximum energy. I just substitute PF, just calculated, to this formula, and I have some creepy formula from energy, maximum energy, which from N. So we have electron density here. That's why Thomas-Fermi model is some pre-density functional theory. So it's some. It was first step, and then based on the step, Hohenberg-Kohn created density functional theory. So we have this energy from N, from electron density. Electron density is very useful because we don't need these huge wave functions. We can somehow plot this electron density because it's something with only 3 coordinates, x, y, z. It's something which exists in 3D space. So we just need x, y, and z coordinates, not a lot of coordinates of each wave function. And that's why it's even more useful than a Hartree-Fock method. Because in Hartree-Fock method, we have dealt with all these electrons one by one. And here we deal only with electron density, which depends on 3 coordinates. And we have this electron, this maximum energy, and now I want to take some kinetic energy and potential energy from electron density. I want to derive these equations. First of all, I will begin with kinetic energy of electrons. So I will write it in this form. It's some integral over the space. It's some kinetic energy density, dr. Kinetic energy density, what is it? It's just kinetic energy divided by volume. It's a rather simple thing if you will follow it step by step. What is kinetic energy density? T divided by V. V is volume of one small cube. Then it's just integral from energy P squared to M divided by 2M. What is N? We have N number of electrons. We can substitute it here and take first derivative from N. And we will get such integral from just P, from just momentum. I will take all this 2M for P here from the integral, and I will get rather simple integral. P in the power of 4 dp, and integral from 0 to pf. So it's integral in all this space, in all space filled by electrons, and some constant before it. And I'll get this kinetic energy density of electrons, of each electron inside this square. Then, of course, I can substitute pf here and get this kinetic energy density from electron density. And it's very useful and very important formula, which calls local density approximation. And from this local density approximation have grown density functional theory. You see, we have some kinetic energy, and we assume that it depends on N, on electron density. Then we make all these calculations, which I showed you, and then we can tell, okay, all this this kinetic energy from real world, it's a real world kinetic energy, we can approximate it by some local density approximation. What it means? It means that we take some place where this electron density is stable, it's constant. That means that we take some square, and we tell that inside the square, inside the sphere, the number of electrons is stable because we have assumed it before. Number of electrons is constant. That's why electron density is also constant. We don't know what happens in the other places, but we know that here locally in this place, number of electrons is stable, and that's why we have constant electron density. That's why this approach is called local density approximation, because we take these spheres and say that inside the spheres, electron density is constant. And then I can also divide it into one electron. I can from here I can take one single particle local density, kinetic energy, and I showed you just how to do it. Single particle. So we have it's real world. It's inside the sphere, and it's for single particle. Kinetic energy of single particle, and we have such beautiful formula. Some constant integral from nr in the power of 5/3. That's local density approximation. That's how kinetic energy of single particle, single electron, depended on this electron density. And that's how we have a last питання. Okay.
How do you actually derive
this formula? You should take this PF and insert here. Insert here, and then you have this integral, and you say that this huge T, it's like integral from this T from, so it's 1/3, you see 1/3, and here it's 5. So we will have power 5/3. So we have calculated kinetic energy of single electron inside electron gas. It's very important thing. And last week, when we have calculated our silicon crystal, we have used this approach. We have used a low density approximation. So kinetic energy in our crystal was calculated by this formula, which was solved by quantum espresso by computer methods. Okay, but kinetic energy is not all. Also, we have Coulomb energy. It's some electron interactions, and it's Hartree energy. We have seen it before. It's just interaction from one electron, which describes by electron density in some region R, multiplied by electron density. It's another electron, which describes by electron density in some point R prime, divided with R minus R prime, and we have this beautiful formula, Hartree energy. So in Thomas-Fermi model, we have some potential. So it's the energy. It's the energy. We have kinetic energy, which we approach by this single particle, low density approximation. Then we have Hartree energy, electron Coulomb interaction, here Hartree energy, and we have some external potential. And I told you about this external potential when I stated the problem of this uniform electron gas. And it's just how we can show the interaction between electron density, between electrons and this external potential by such integral. We don't know the form of this integral, but it will be some integral. So that's how we can calculate this energy of our electron gas in Thomas-Fermi model. Kinetic energy by LDA, Hartree energy, and some external potential. And I just have substituted each formula. So I have substituted LDA, single particle here, and in the power of 5/3. Then I have substituted Hartree formula, Q squared. It means it's just Coulomb interaction. And I have substituted this potential, just external potential with which interacts with electron density. So this is the energy of the system by Thomas-Fermi model. But it's not okay. So it was okay in 1930s. 1930s, it was beautiful theory, and some people had calculated it by hands. So they had they don't have any computers, and they made some parallel computations before it became mainstream. So they took a lot of scientists who just took these equations and have solved it iterationally. And then they checked each other each day, and they have computed a lot of materials. It's just thing. And the results was rather okay. So it was maybe 20% of error to the whole energy, but from one side we have situations when we can't solve Schrödinger equation and we have no idea about the energy, and from other side we have energy with error some 20 or 30%. So second situation is much better. And this situation lasted in till 1960s. And here you can see some comparisons with different methods. HF is Hartree-Fock, TF Thomas-Fermi, and here in this paper they calculated atomic energies using various Thomas-Fermi type models. Okay, we have a lot of Thomas-Fermi models. We have Thomas-Fermi Dirac. It means that we have added spins here. I don't know what is W. Okay, it doesn't matter. We have some variations of this method, and I told you about this, about the core method and Hartree-Fock method. And we can see the energy calculated. We can see that all these methods, they are rather different. Minus 0.7, minus 0.5. It's huge difference. 50% difference. Helium minus 3.8 energy, electron volts, minus 2.8. So we have huge difference between these methods. And we have, okay, you see the problem. Yeah. We have a lot of methods and we don't know what is correct. But all the methods, it's not like here is 0.5 and here like 100. They are rather close. They not so close as we want, but they are rather close. So it's not like 10,000.
Same orders of magnitude.
Same orders, yeah. Minus 3.8, minus 2.8. But this situation is awful, and we should. Oh, it's here is some calculation of radial density of wave function using different methods. Hartree-Fock. By the way, Hartree-Fock shows rather good results. So even now, some guys use Hartree-Fock, and I will tell you then about hybrid functionals. And hybrid functionals, they take some part from density functional theory and take some part from Hartree-Fock. So Hartree-Fock is rather good method. It was first method. Then it was Thomas-Fermi. Okay, honestly, I don't know which was firstly, because they was almost at the same time. It was late 1920s, and one should make some huge historical research to tell what was first. And I think, it was parallelly. It was two different methods. Why we have told so? I have told so much about homogeneous electron gas, because in 1964, these two guys, Pierre Hohenberg and Walter Kohn, have written a paper in Inhomogeneous electron gas. So they just took Thomas-Fermi method. You see all this formula which I showed you: the air and air, the air plus something, and some potentials. Air goes to infinite. So we can see some things from Thomas-Fermi model, and they took Thomas-Fermi model and improved it. They improved it to some more closer to reality case, to inhomogeneous electron gas. And this is, you see, scientific articles, 39,000. I made the screen today in the morning, and maybe now we have more science. So it's the so this paper is the beginning of density functional theory, made by these two guys. And you see that they lived till 2017, 2016. So these guys lived not so many time ago. Walter Kohn, he was born, as I know, in Austria, and he was Jew. And it was it was a problem at the time, because in 1938 Austria was annexed by Germany, by Nazi Germany, and Walter Kohn with his family had to move from Austria, and it was some story that he almost got to concentration concentration camp as a Jew, but he was saved and he go to Canada. Then there he go to university. Then he moved to Caltech, to California, and then he got Nobel Prize for his theory, which we call density functional theory. Pierre Hohenberg was his collaborator from France, and next week we will tell about another third collaborator, Luchem, who was postdoc in the group of Walter Kohn, who also made some improvements to this theory. But today we will tell only about these two theorems, which became basis of density functional theory, and about this this article. It's, by the way, it's a good thing to read these original articles, original historical articles. It can be rather interesting. Okay. First, Hohenberg-Kohn theorem from this article. The external potential V external from R is, to within a constant, a unique functional of electron density n. Since in turn V external fixes Hamiltonian, we see that the full many particle ground state is a unique functional of nr. I think that this formulation is not. It's rather hard to. It's rather hard to deal with this formulation. You can say it in other words. Ground state electron density uniquely corresponds to many electron ground state wave function. So we have, if we have some electron density of the lowest energy of ground state energy of some system, we have lowest energy. We have some electron density of this lowest energy state, ground state, and we can say that we have only one wave function which can create this electron density, because electron density is psi multiplies psi complex conjugated, and we can take some different kinds of these psis and create the same electron density. But these two guys, they showed that if we deal with ground state, we have only one wave function which corresponds to one electron density. And the second theorem, the total ground state energy can be calculated as a functional of ground state electron density. So they are connected. Here we say that we have some wave function which create, we have some electron density which corresponds to unique wave function. And here we say that all we need to calculate energy of this state is this electron density.
Just follows from Schrödinger equation.
No, it's not obvious false from Schrödinger equation. Yeah, of course, they will. Now I will show you the proof of these theorems because it's rather simple, this proofs. But we can play with these wave functions and create with different wave functions the same electron density. Because wave functions is something which creates from a lot of electrons, ions, and some other things, and we can move these electrons. We can take another interactions, but we can create some mathematically. We can create some theoretically, mathematically. We can create some wave functions which will some different wave functions which will give some different electron densities. But here we tell them only about ground state. Ground state is all we need. Maybe on not ground state, the situation is different. But all we need is ground state. Okay, how to prove it? So external potential, we have it. A unique functional of electron density. We have electron density nr, n number of electrons. Psi is some wave function of the ground state, E ground state energy and H Hamiltonian. And let's consider some, okay, I will make this proof ab absurdum проти відзворотнього. Yeah. So, V external, ні, ab absurdum це щось інше. Okay. Okay, let's consider another system with V prime external potential, which don't equal to V external plus C to within a constant. It's just some constant. So it's some different external potential. And we have some other VC prime, we have N prime, C prime, E prime, and all other primes. So we will consider another system. And we think that this system, okay, if we, from our first system, we can calculate ground state energy. How we can calculate? It will be bra psi, Hamiltonian, ket psi. And as this is ground state energy, if we will take for the same Hamiltonian some another psi functions, we should say that this thing will be more than this because it's ground state energy. It's the minimum energy. C primes is some another wave functions which theoretically can create the same electron density. Okay, I just take this Hamiltonian. It's kinetic energy plus some potential energy like Hartree energy and V external on N strich R, on N prime R. And H prime, the same things. But here, okay, here should be just normal, and should be just normal. And here, psi prime and prime. And I will substitute it. What I will get? No. So it was correct. And prime here and prime here. What I will get if I will substitute. Okay, I want to take H. It will be like H prime plus V external minus V prime external multiply on this NR. The R. I missed the, but here is all correct. I just took a Hamiltonian, original Hamiltonian from this prime Hamiltonian for some other system. And what I get? I get this energy prime, C prime, H prime, C prime, plus some difference of external potentials. And we think that these external potentials, they are totally different. They're different more than a constant. Because if they will be different on a constant, we don't have anything interesting. It will be just constant. And shortly, ground state energy should be less than some prime energy, which is also ground state energy for some another system, plus this thing, plus this term. We can do it in reverse way. We can start from I hope you understand all this thing. So we have two systems. One system, psi H psi, and it has the lowest energy E, and another system with another external potential, which has the lowest energy E psi, E prime, with psi prime, H prime, psi prime. And I want to show that we can't, and I want to show that I can't create two external potentials which will make the same ground state energy. So that this correspondence should be unique, and we should have this external potential, and which will be correspondingly, which will correspond to some unique NR. And I got these two equations. In one equation, E less than E prime, each of these energies is the lowest energy of the system, plus some term. And here I have the same, but reverse. E prime less than E, plus some plus some term which will be always the same, except we have different signs for potentials, and we have different n electron densities. And that's why we have some contradiction. Because as you see, E plus E prime should be less than this thing plus this thing. So this integral should be more than 0. But we can, when we okay, this integral should be 0 to make this correct. To make all the statement correct, this integral should be 0. But we know that these potentials, they differ from each other. That's why they can make 0, because they are very different. They differ more than like potential plus constant. That's why we should make this 0. And we can achieve it only one way, when we say that electron density of our first system will be the same electron density as the electron density of the second system. That's why we get this rule correct, that each external potential corresponds to only one electron function, to only one electron density.
You said that in order for this statement to be true, we need to have this integral equal 0.
More and equal, yeah.
Well, but if it's not 0, it can still be less.
If it's not 0, if it's okay.
If it's just less, if it's just smaller than the right part, then it's not necessary for it to be 0.
Yeah, but here and here you see the same thing. So I can just move it, and I will have conditions that this electron should be more or equal to 0.
Yeah, but it can still be more than 0.
It can be still be more than 0. Maybe I missed something. Maybe I missed the same equation, but where I will have E plus E prime more than E plus E prime plus this integral.
Okay.
And in that way, we should say that it can be true only if you have n prime equals to nr. Yeah. Okay. This looks not so hard. And another theorem, that the total ground state energy can be created as a function of ground state electron density. First theorem tells us that we have some unique electron density, which corresponds to some unique wave function and to some unique external potential. And then we take this unique electron density of ground state, we tell about ground state, substitute it to some equation, some functional of energy, and we'll get ground state energy. So this En, E from N, this energy functional, it will consist of three parts. As the same thing as it was in the Thomas-Fermi. Kinetic energy part, Hartree part, and external potential part. Now for TS, single energy, we will have some kinetic energy which depends on some electrons, electron 1, electron 2, electron 3, psi functions of these electrons. Hartree, some external potential, and some mystical term XC, which calls exchange correlation term. So it's exchange correlation functional, and we don't know it exactly. We can calculate rather good kinetic energy, we can calculate rather good Hartree energy and this energy. But we don't know the exact form of exchange correlation. And why we get it? So from what deeps of physics it appeared? It appeared from two rather simple things. When we take this T, for this functional T from N is kinetic functional for real system, for real with no approximations. Then we approximate it by single electron kinetic energy, local density approximation from Thomas-Fermi model. We can approximate it with some with a lot of ways, but I told you about Thomas-Fermi. Okay, so let it be Thomas-Fermi, and it will be not ideal. It's some approximation to the nature, to this functional, and we'll have some correlation term. So we have this single particle kinetic energy, and we have some kinetic energy of all other system, and we tell it, and we name it correlation term. So correlation term rise from some Coulomb interactions between these single particles. When we divide this real world real world kinetic energy functional into two functionals, just to calculate it: single electron and some other things. And exchange term, correlation term goes from kinetic energy, exchange term goes from potential energy. We also approximate this real world potential energy with some Hartree energy, with just Coulomb iteration, and all other things. We don't know what these things are, because this is approximation. This is real world, and this is something we don't know what is it. But we have a name to this unknown term. We name it exchange term, and both terms usually people don't divide them. So they took both and tell that and name it exchange correlation term, some functional, because we don't know this, and what's the difference if we will take two terms or we will have one term? That's why we call it exchange correlation term. And this exchange correlation term is some bad thing, because we can't we don't know it. We even don't know how it looks like, and that's why we can't create some energy functional which will consist with nature exactly, because of this term. Because all these things are approximations, but they are good approximations. And the last slide, some some final words. Now we are looking on the world from the side of Hohenberg-Kohn theorems. It's not density functional theory yet, because for density functional theory, I should give you one other lecture with Kohn-Sham equations. But Kohn-Sham theorems are rather important for it. Okay, so we have some ground state electron density, F equals 3. It's like degrees of freedom. X, Y, Z, because R is a real world, some real world vector. 3 degrees of freedom. From this to this ground state electron density will uniquely corresponds some external field. External field, it can be some field of ions in the system. So when we have calculated silicon, diamond silicon, we have 2 atoms in the unit cell, and each atom had 4 valent electrons. And all other things, so we have 4 valent electrons and 2 ions, 4 valent electrons for each atom, and 2 ions. Each of this ion with another electrons create some external field where this valence electrons moves. It also has 3 degrees of freedom. This external potential leads to some Schrödinger equation. And from this Schrödinger equation, single particle Schrödinger equation, from this Schrödinger equation, we can get some psi functions. We don't know them. It's really hard to solve it, but I will show you how to do it next time. And we will have 3n degrees of freedom. N is the number of electrons. It can be huge. And then from this, we have, so we don't know it. It's crazy. This is also crazy. Ground state wave function, it's also crazy because it also consists of 3n. But when we go from this, to ground state, we just discard this n, and we have only 3 degrees of freedom. That's the reason. That's why we can use Hohenberg-Kohn theorems and then density functional theory to calculate a lot of properties, a lot of materials, because we don't use this infinite number of freedoms. We can use only 3 number of freedoms, and that was the idea. And for that, Walter Kohn got Nobel Prize, and also for Kohn-Sham equations, which will be the topic of our next lecture. So you can ask some questions if you have.
I have a question. So we are calculating only ground state wave functions and density. Does it mean that, for example, like we are assuming that the temperature is 0, so
yeah,
we're only calculating below the Fermi level.
Mm-hmm.
So, like for a semiconductor, we cannot really know what's happening in the conduction band.
We can do it. We can do it by.
We're just shifting the Fermi levels.
We can each band in semiconductor or in conductor, it calls Kohn-Sham band, and we can just add some 0 Kohn-Sham band. So in semiconductor we will have this valence bands which will be filled by electrons, but then in calculations we can add some free bands which will be without electrons. And then we can populate this bands with some functions. So I will show you in quantum espresso. We had to choose these functions, how we will fill this free states. So it's like it's some fictional mathematic trick to calculate, but it gets to good results. Okay, if you don't have any other questions, we can have a few minutes break, and then we have practice. Another question?
No, it's not really.